Okay, so let's start, continue with our discussion of the common source amplifier. So let's start with the problem. So calculate the small signal voltage gain of a CS amplifier shown below. So here is the circuit, the simple resistive loaded amplifier that we looked at in class. Input is applied at the gate of the transistor, output is taken at the drain of the transistor. RD is connected between supply, so this is your supply. Supply is 1.8 volts. RD is 1 kilo ohm. The W by L of this transistor is 10 by 0.18. Okay. So it is given that ID is equal to 1 milliamp. That is the current flowing through the resistor. You're also given mu n Cox is equal to 100 microamp per volt squared. VTH of the transistor is half a volt, and lambda is equal to 0. Okay. So first thing is calculate the small signal voltage gain of this amplifier, and the second part of it is verify that, let's call this transistor M1, verify that M1 is in saturation. So I'll give you a few minutes. Tell me what the gain of the transistor, what the small signal voltage gain is, and how did you verify M1 is in saturation?
Sure, is the gain minus 3.33?
Good. Okay, so we know that lambda is equal to 0. So let's first draw the small signal model of the circuit. So small signal model of the circuit, again replace M1 with, so let's first assume that M1 is in saturation. So if M1 is in saturation, right, let's replace M1 with its small signal model. So this is your gate, source and drain, right? So drain to source, I have a current which is given by GM times VGS. This voltage is VGS, right? Lambda is equal to 0, so R0 is infinity. And then now if I take the gate is connected to V in. Source is grounded. Right? The drain is connected, the voltage is pulled out at, output voltage is pulled out of the drain. I have RD connected between drain and VDD. For a small signal model, VDD is ground. So I essentially have RD connected to ground between drain and ground. So remember, this is small signal ground. So I'll sometimes call VDD, power supplies, are small signal grounds. So they're not actual ground for DC analysis, but for AC analysis, they are signal grounds. Right? And so now V out can be written as, so the current, if you look at KCL in this, KVL in this loop, right? V out is given by minus GM VGS into RD, and VGS is nothing but V in, and so therefore I have V out by V in is equal to minus GMRD, right? And this is nothing but your small signal gain. So you need to calculate, RD is given to you, RD is 1 kilo ohm, so you need to calculate GM. So how do you calculate GM? You know what the drain what the DC current ID is flowing through the circuit, right? So if I know ID, I know mu n C ox, I know W by L, I can write my GM as square root of 2 mu n C ox W by L times ID. Right? Substitute the terms. This works out to around 1 by 300 units of GMR moles. And so therefore the gain is given by minus 1 by 300 into 1000, which is minus 10 by 3 or 3.33 volt per volt. Right? So that is the small signal gain of this circuit. So, and if I give a 10 millivolt signal at the input, I'm going to get a 30 millivolt signal at the output. So how do I verify if M1 is in saturation? What is the condition to check to prove that M1 is in
So you're
saturation?
showing Vn and then Vn is VGS, right?
Vn and VGS are different. Remember, VGS is the DC voltage that is connected. Vn is the small signal AC voltage, right? So, yeah.
VDS should be greater than V overdrive.
Correct. Very good. So you need to, so to check if M1 saturation, to check if M1 is in saturation, you need to confirm that VDS is greater than or equal to V overdrive. V overdrive is nothing but VG minus VT. So how do you, so you need to check this. So how do I find out V overdrive? How do I find out V overdrive? How do I find out VDS?
So you can get V overdrive from GM.
Correct. Right. So either GM or ID, right? So you know M1 is, so assume M1 is in saturation. So if M1 is in saturation, then you know that half N prime W by L V overdrive the whole square should be equal to ID, which is 1 milliamp, right? So that would give you V overdrive. And V overdrive works out to, has anybody done the calculation? What does V overdrive work to? So V overdrive will work to 0.6 volts. And how do I find out VDS? How do I find out VDS?
VDD minus IDRD.
VDID minus IDRD, right? VDD is 1.8, ID is 1 milliamp flowing through 1 kilo, so there's a 1 volt drop here. So VDS is 0.8 volts. So since VDS is greater than VOB, the transistor is in saturation, and therefore our model is correct. And so we can stick to that. Our small signal gain is, so our modeling is correct, right? And so the small signal gain remains 3.3 volt per volt. Okay. Now let's talk a little bit about two other parameters which I'd like to introduce about the amplifier. So we spoke about a voltage amplifier. So this common source amplifier, we're using it as a voltage amplifier, right? I give in a V in at the gate and I get a V out at the output, right? So now let's talk about the voltage amplifier. So in addition to the gain, we have to talk about Rn and Rout, right? So for a voltage amplifier, if I want an ideal voltage amplifier, what should Rn be and what should Rout be? So if I want
Rn
an
is infinity and Rout is 0.
Very good. So Rn is infinity and Rout is 0, right? So you want, so now let's look at our circuit. Now remember, when you're doing voltage amplifier, what are these Rn, Rout? These are nothing but the small signal input resistances. And this is the small signal output resistance, right? So how do I calculate the Rn and Rout for this circuit? Right? So you again go back to the small signal model of the circuit. So let's draw the small signal model of the circuit. So it is given by Vn. So I'm going to draw it directly now. GM VGS This is VGS. This is V in. Right? This is my source, which is grounded again. And then I have an RD connected to ground here, right? And this is my V naught. So if I want to calculate R in, how would I go about doing that, anybody? If I want to calculate what the input impedance is, what does an input impedance mean? That is, what is the resistance I see if I look into the input node? So how do I calculate that?
So VGS by IGS. But
Yes,
since
correct,
IGS
right?
is 0.
So basically, if I can calculate what is the input small signal current flowing through the circuit, then my Rin can be given by V in by I in, right? So this is the input resistance of the circuit. Now in this case, what is I in equal to?
0.
I in is 0, right? Remember, it's connected to the gate of the transistor, right? And the gate of the transistor is an insulator. So right now, because we are not looking at high frequency models of the transistor, we don't have to worry about the capacitance at the gate. So right now, your IN is 0, and therefore the Rn for this circuit is infinite, right? Because you've connected that input signal to the gate of the transistor, and the gate being an insulator, you are able to get this high Rn. Okay, so now let's calculate what happens. So now let's calculate the R out. So let's calculate R out. So what does R out mean? R out means what is the resistance seen by the output side of the circuit when the inputs are grounded, right? So what does that mean? So when I want to calculate the R out, what you have to do is apply a V out at the output node and measure I naught, or measure the current flowing at the output, and before you do that, you have to ground or set all the inputs to 0, right? So in the case of input voltage, you set the input voltage to a short circuit. In the case of an input current source, you set the input current to an open circuit, right? So again, what are we doing here? So if I go to calculating R out, what I want to do is, let's again look at this circuit.
So could you go to the previous page
One
once?
sec.
Thank you, sir.
Yeah. So what I want to do now is, I want to apply a voltage V0 here. Want to measure the current flowing into the output. And I want to, so when I'm doing the R out, so to calculate R out, I will set my input signal to 0. So I will ground this. So if I ground the input, what happens to VGS?
0.
So VGS is 0, right? So if VGS is 0, what happens to this current source?
That also 0.
That is also 0. So that also moves away from. So then if I now calculate V out by R out, what is that equal to?
So RD.
RD, right? So you see that in this case, the output resistance of your amplifier is RD. So now if you think about it, if you now think about the common source amplifier, your for lambda equal to 0, your gain is given by GMRD, your Rin is given by infinity, your R out is given by RD. Now see one of the problems of the circuit. So for an ideal voltage amplifier, right, you want R out to be as low as possible. To get a good gain, what do you want RD to be?
Close to 0.
No, so R out you want, so if I want a good
Very
voltage amplifier, I want RD to be low. But if RD goes low, then I'll get a low gain, right, for the same GM. So if I fix the current in the circuit, then what happens therefore is I have to trade off. So this circuit, if I want to get a high gain from the circuit, I need to design a circuit with high RD. But if I design a circuit with high RD, then I'm going to have a high R out. And you guys know, you've done that in the last tutorial. When R out goes high, then the usable output signal actually reduces, right? Because you have a lot of the output signal dropping within the amplifier rather than outside the amplifier, right? So this is one of the trade-offs of this design. So you need to figure out how do we break this trade-off. Right? Now, why don't you guys do this for me and tell me what happens? So if lambda is not equal to 0, can you tell me what the values of AV, Rn, and Rout would be? Take 2 minutes and solve it and tell me. Same circuit, if I assume lambda is not equal to 0, what is the value of AV, Rn, and Rout?
Rn should be the same.
Rn should be the same. What about AV?
So R out will be RD
RO,
and
RD.
RO in parallel.
Rout will be RO parallel RD. And what about AV?
Minus GM into RO parallel RD.
Good. Right? So again, what you see here is that eventually, even if you make a good transistor, suppose your R0, so problem is that R0 is high, right? But R0 therefore is getting colored because of this RD. Because of RD, what happens is your net resistance actually starts dropping. Everybody, by the way, is able to do this, right? I don't have to solve this for you. Please let me know if you can't solve this. Everybody is able to get R out to be R0 parallel RD. So this technique of looking into, so I use these phrases, looking into this node, what is the resistance, looking into, so you should be able to calculate the resistance looking into any node of the circuit. So that is something which you should be very familiar with. For now, you can use the small signal models. Eventually, when you look at the MOS transistor circuit, you should be able to tell exactly what's happening. Okay. So any questions so far?
But looking into just means the other side voltage sources or some current sources
Yes,
should be just
yes,
turned off, right?
yes.
Yes.
Okay. Any questions so far? Okay. So let's think a little bit about this configuration again. And let's try and see, can we do something better than what we've done so far? Right. So now the problem with this configuration, we saw that is that this RD is the problem, right? You want a high RD to get, so to get high gain means you want RD to increase, right? But for low R out, you want RD to be low, right? So how do we fix this issue? So let's think about another circuit, right? And you guys tell me what happens to the gain of this circuit. So now consider a circuit given in figure A.
So sorry to interrupt. Can you just go back to the last slide for a while? Thank you.
Okay, so let's look at this circuit. So instead of the resistor, I'm replacing it with the current source with some current I flowing through that, right? Now, if lambda is not equal to 0, can you tell me what the gain of this circuit is? So what I've done is I've replaced RD with the ideal current source. So I've replaced RD with an ideal current source. Can you tell me what happens to this circuit? What is the gain?
Won't the gain be 0?
Think about it carefully. Small signal voltage gain, I'm asking. What is the meaning of an ideal current source?
No resistance.
No resistance.
No resistance. Zero resistance.
Zero resistance or some other thing? If you look at so current source, we now look at the Norton equivalent, right? So what is the resistance?
So it just means that the source will maintain that same current in that branch.
Correct.
It won't allow it to change.
Right. Anyway, calculate the gain and tell me if anybody can. If not, we'll do it together. Use the same logic. Replace M1 with its small signal model and tell me what the gain should be. So when you do small signal analysis for a voltage source, we grounded it. For a current source, what would we do?
Open the current source.
Open the current source. Very good. So do that and tell me if you can calculate the gain.
It's minus GM R naught.
Very good. What about Rn?
Infinity.
And R out?
R naught.
Good. Okay, let's see how we did that. Good. So again, replace M1 with its small signal model, right? So if you replace M1 with its small signal model, remember lambda is not equal to 0. So this is your small signal model. This is your drain, that is your source, right? This is your gate. The gate is again connected to Vn, right? The source is grounded. Now the drain is connected to a current source, right? So when you're doing small signal modeling of the current source is going to be an open. So what happens therefore is that the current source, basically you have an open circuit between the drain and the supply. So what you're seeing therefore is that this is the small signal model of this circuit, right? This current source, because it's an ideal current source, right? It presents infinite resistance. It's an open circuit for small signal analysis, right? And so now if you look at this, now if you want to calculate the gain, if you look at this loop, right? GM-VGS flows through R0 only. So your V0 is given by minus GM-VGS R0, right? And VGS is equal to Vin. Therefore, your AV is given by V0 by Vin, which is minus GM R0. Right? So what happens in an ideal transistor? So if I had an ideal transistor, long channel transistor, what is the value of R0? For a long channel transistor with no channel modulation, what is the value? Yes. And so what happens to voltage gain if this becomes an ideal transistor? Infinite, right? So you can get infinite gain from the MOSFET provided you're able to create an ideal current source, number one, and if you don't have channel modulation, both of which are not true in real life, right? But what I'm trying to get at is the way to build a better amplifier in this topology is if you can find a way to replace the resistor with an ideal current source. If you're able to replace the resistor with an ideal current source, then you should be able to get a high gain. So remember here in this, your gain was minus GM RO parallel RD, right? So whatever, and in most cases, RO is a high number. So when you see RO parallel RD is always going to be less than RO. Right? And so therefore what you see is, because RD is normally less than RO. So therefore what you see is that if I'm able to replace this resistor with an ideal current source, then I can get the maximum gain. So one of the ways by which I can improve this amplifier topology is by replacing RD with a current source, right? So how do we do that? So what current, so how do we create a current source using transistors? Do you guys know of any way by which I can create a current source with a transistor?
Another transistor in saturation.
Very good. Right? The simplest way to create a current source would be if I replace this RD with another transistor in saturation, right? Then that transistor in saturation behaves like a current source, right? So let's look at the next topology in common source, and this is known as a current loaded CS amplifier. So what we'll do is we'll replace the load now. Bear with me now, and in the tutorial we'll look at what happens if I do an NMOS. So right now I want you to replace the suppose I've given it some DC voltage, some bias voltage, such that M2 is in saturation. So if I now consider this circuit, right? So now let's consider this circuit and let's think about what is the gain. So what do I want? So how do I pick this bias voltage? How do I ensure that this transistor is in saturation?
So VB minus V out must be greater than VB minus V2.
Correct. So to ensure M2 is in saturation, remember this is a PMOS, right? If this is a PMOS, you want your VDS to be less than VGS minus VT, with all numbers being negative. Remember, PMOS, VDS, VGS are all negative, right? So if you look at VGS, where is the source of this PMOS? What voltage is it connected to? If you look at the M2, which is a PMOS, where is the source connected?
So we out.
No. Where is the source? What does the arrow signify?
Source is where the arrow is.
Yeah, and the arrow is connected to which terminal?
VDD.
VDD, right? So this is the source of the PMOS. This is the drain of the PMOS. This is the drain of the NMOS. And this is the source of the NMOS. Everybody following this? This is a key point here. And that is why I've shown this with the source. So whenever we use PMOSes in circuits, and remember this throughout this entire academic this year, calendar year, PMOSes will always be connected towards VDD. So when you connect the source of the PMOS, because we're using positive voltages, if I connect the source of the PMOS to the highest voltage in the circuit, then my VDS and VGS automatically become negative, right? Similarly, when I connect the source of the NMOS to the lowest voltage in the circuit, my VDS and VGS will automatically become positive. So,
So why did we choose M2 as a PMOS?
Yeah, I will do that in the tutorial. We'll compare if I use an NMOS, what happens, and PMOS, what happens. So wait for the tutorial next week. We'll do that. Or if you want, you can replace it and come back next class and tell me what happens. Do you see any differences between the two? Okay. For now, let's consider the circuit. Let's analyze the circuit and we'll come back to that. All right. So now what is the VGS for M2? So VGS for M2 is given by VB minus VDD. Right? And VDS for M2 is given by Vout minus VDD. Right? And so we want to always ensure in this case, so we will pick VP in such a way that VDS of this MOSFET is less than VGS minus VTP. Remember, VTP is a negative quantity. VGS is a negative quantity. Okay. So how to choose VP, it's important to remember that. Okay. So you would choose it in such a way that, so if I'm going to write it, so VDS is nothing but Vout minus VDD is less than VGS is VB minus VDD minus VTP. Right? So Vout should be less than VB minus VTP. So that would be the condition you'd have to ensure to keep M2 in saturation. How do I keep M1 in saturation? So this is for M2 in saturation. To keep M1 in saturation, what should I do?
Sir, here the V out and the V in are the DC voltages, right?
No, so yeah, these are all the DC. So think about this as two voltages. There is an AC voltage small signal V out and a DC voltage V out. Similarly, V in. So to keep M1 in saturation, how do I keep M1 in saturation? What is the DC voltage condition I need to satisfy? How do I keep M1 in saturation? It's an NMOS, right?
V
What
out
should I
is
do?
greater than
Good.
VGS.
V out is greater than V in minus VTN, right? So the reason I'm saying this is when we'll do design in tutorials, you'll see that it's important for you to also decide what the bias voltages are. So you need to pick the bias voltages carefully so that you ensure the bias point of the circuit is right? So now let's try and figure out. So let's assume M2 and M1 are in saturation, and let's try and see. So again, assume lambda is not equal to 0 in both cases, so for both M1 and M2. Can you find what the small signal gain of the circuit is? Remember, this is a DC voltage, okay? Can somebody calculate the gain? We will do it. If you want to take 2 minutes and try to attempt it first, then I'll solve it with all of you. Let's again calculate all three. What is the voltage gain of the circuit? What is Rn and what is Rout?
So minus GM of NMOS multiplied by R naught parallel of NMOS and PMOS.
Good. Very good. So this is minus GM1, RO1 parallel RO2. Right? I've called this M1, M2. So what is Rn?
Again, infinity, sir, because
Good. Good. What about Rout?
RO1 parallel to RO2.
Very good. Okay. So let's try and solve it. Okay. Let me do it with you. So again, that's your, let's redraw the circuit here and let's replace it with its small signal models. So this is VDD. This is V out. This is your PMOS connected to a DC voltage. This is your NMOS connected to VN, M1, M2. Okay. Remember, drain, source, drain, source. So now let's first replace the NMOS with its small signal model. So the NMOS with its small signal model is here. BGS1, GM1, BGS1, RO1, right? This is connected to the source here. This is gate. Gate is connected to Vin, right? Now the drain of this transistor is connected to the drain of M2, right? So let's now draw the model for M2. Right? So now M2, again, it's gate and this is the source. So this is gate of M2. This is source of M2. Remember, in the PMOS, the current direction is going to be opposite to that of the NMOS, right? So this is your BGS2. This is GM2, BGS2. This is your RO2, right? So this is source. Now the drain of the PMOS is connected to the drain of the NMOS, right? And so this is where your output voltage is taken. VDD source is connected to VDD. VDD is a DC voltage, so this is grounded, right? The gate of the PMOS is not connected to a small signal. It's connected to a DC voltage. So for small signal analysis, this gate is also grounded, right? So therefore, if you look at M2, VGS2 therefore is equal to 0. So because VGS2 is equal to 0, this PMOS current source disappears. So what does this look like? So therefore, this circuit essentially looks like you have connected a resistor RO2 to M1. So if you think about this, this essentially looks like I've just replaced the RD with an RO2, right? And so now if I look at Vout, right, I can write my Vout as, Vout is nothing but minus GM1, VGS1. This current flows through a parallel combination of R01 and R02 because see, R01 is connected from Vout to ground. R02 is also connected from Vout to ground, right? So R01 and R02 are essentially parallel to each other. So R01 parallel R02, right? And VGS1 is nothing but Vin. So therefore my gain is given by minus GM1 R01 parallel R02. Right? So this looks very similar to GM RO parallel RD, right? So what this M2 is doing is, because of the fact that you've connected M2 in saturation, M2 in saturation is offering an equivalent small signal resistance of RO2. Right?
So could you explain the Vout once again?
Okay. What didn't you understand? So Vout, if you look at this current is going to flow through RO1, right? So if you look at RO1 and RO2, RO1 is connected between Vout and ground. RO2 is also connected between Vout and ground. Therefore, RO1 and RO2 are parallel to each other. And what is the current flowing through RO1 parallel RO2 combination? It is nothing but GM1 times VGS1. So the net voltage at the output, it's going to be minus GM1 times RO1 parallel RO2 times VGS1. Right? So GM1 VGS1 is the current that is flowing through the parallel combination of RO1 and RO2. And so therefore, if I think about the gain is just given by this. Okay. So what you see here is that
so how is VGS to 0?
When you're doing small signal analysis, what do you do to a DC voltage source?
Oh, okay. So VB is
right. So the gate of M2 is grounded. We look at a condition when that doesn't happen, but in this case, because I've applied only a DC voltage to the gate of M2, right? When I do small signal analysis, this gate is essentially works like a ground. So let's go back and think about what are we doing? We are applying. Let's logically think what's happening in this circuit, right? We are applying a voltage. So let's look at the NMOS. At NMOS, right? NMOS is in saturation. So when I apply an AC voltage to the gate of the NMOS, right? I am modulating the current flowing through this NMOS. I'm modulating current flowing through the NMOS, and hence I get a gain because that current is flowing through its internal resistance of R01. Now, if I look at this PMOS, I'm not applying a small signal voltage at the gate. So if I look at the PMOS has a constant VGS, right? VGS is not changing for the PMOS. What is happening when I apply a small signal at Vn is I'm changing the value of VDS for the PMOS, right? I'm not changing the value of VGS, right? And now because this PMOS, I biased it in saturation, this PMOS looks like a current source. So what does the current source mean? Current source means that it supplies a constant current no matter what the voltage across it is, right? And so therefore what's happening with this PMOS is this voltage as it fluctuates, right? It is essentially looking like this PMOS is just being replaced by a small signal resistor. So this PMOS is just working like a current source, right? If I had a very long channel PMOS whose R0 was very, very high, then this would have looked like a perfect current source. Now, because of the fact that lambda is never 0 in real transistors, we have to always consider that MOSFETs in saturation will be close to a good current source but are not good current sources. Right? And so essentially what you've done is that instead of having an RD here, I've replaced that RD in your previous topology with a higher resistance, and that resistance has been created artificially. So that is an important thing I want you to remember, is that that resistance has been created artificially by replacing that resistor with a transistor which is biased in saturation. So when the transistor is biased in saturation, right, it offers a small signal resistance which is very high. So there's a difference between the two circuits that we looked at. When we had just pure RD, right, the DC value of RD was also the same. Here, if you look at the DC value of the resistance of this, it's going to be very, very high, right? But what M2 is doing is, M2 is offering a resistance RO2 to the common source amplifier, right? And so what you do is essentially what I'm basically saying is, if I look into the drain of the PMOS, I see a resistance of RO2, right? So I could have easily thought of this as something like this. Now, the reason why I don't draw this with VDD and all is because this is happening only in small signal. So because this is happening only in small signal, I can quickly write therefore the gain as minus GM RO1 parallel RO2. So the key thing again to remember is that the GM that is required here is the GM of the NMOS. The PMOS is not involved in conversion of the current. Right? The NMOS is doing the work of converting the input voltage to an input current. All the PMOS is doing is that the PMOS is providing a load. It's providing an apparent large resistance for the small signal to fall across, leading to a high gain. Is that clear? I want you to understand the difference between the two. It is not the same as M2 is not a resistor. M2 is a current source. That current source in small signal offers a very high resistance to the small signal circuit. Is that clear? Any questions here?
Sir, I have a doubt as to, it would be better if we actually have the ideal current source for the NMOS, right? That way you have a better gain, because
Sure. How do you make an ideal current source?
Yes, sir, that's what I was getting at. Thank you.
So the ideal current source, there's a lot of, if you take advanced analog classes, we do have a very nice circuit which can give us. So a large part of analog design involves trying to figure out how to create this perfect voltage source, perfect current sources. I mean, now you're not even scratched the surface. You have to worry about the variation in voltage, variation in temperature, variation in the MOS characteristics, etc. So creation of an ideal current source, an ideal voltage source is a very complicated design problem. It's not that it's not done. We use that on a regular basis, but you still need to learn how to get there. So once we learn the basic components of design, eventually if you take an advanced analog class, you'll be able to understand how to build these current sources and voltage sources. Any questions?
Isn't this a CMOS amplifier, sir?
We don't call this a CMOS amplifier. We use CMOS technology, but this, again, we don't call this a CMOS amplifier. We don't call this CMOS amplifier because the signal is being given only to the NMOS transistor. So hence we call this as a common source amplifier. So it's a NMOS common source amplifier with an PMOS current load. That would be how I would define this circuit.
Sir, for the last equivalent circuit you drew, what is the difference between this circuit and the common source resistive load circuit we drew? Like both would have been the same.
This is then there's no. So M2, I'm replacing it with its small signal model right now because VP is 0. This current source doesn't come into play. So we'll do an example with. So I was about to get there, but let me do one more circuit and then we'll get there. So
Just adding out like extension to this. What if
One sec. Let me clarify the place. So I hope I'm clear that the difference between these two is that here I have an M2 transistor as opposed to just a simple resistor, right? So I've replaced the transistor with its small signal model. It so happens that because of the fact that the gate of the PMOS is connected DC supply, I end up seeing that this current source really doesn't make any difference. And all that this PMOS therefore is doing is offering an RO2 to the signal. Is that clear? So that's the only difference. So analysis wise, in the small signal, there's no difference. It's just, I could have drawn RD here, it's RO1 parallel RD, instead of RD, it is RO2. But that's what I'm trying to get at is now when you see a circuit like this, where I've connected a current load, you should immediately be able to tell me, okay, this is a common source amplifier, right? It's a common source amplifier where the NMOS is converting the input small signal voltage to a small signal current. That current is flowing through two resistors, RO1 parallel RO2. Hence, the gain is given by GM1 RO1 parallel RO2. Right? So that is how you analyze circuits, because later on when we'll quickly ramp up to larger circuits. So then you won't have time to keep doing these small signal analysis and replace 5 transistors with these small signal models. So understanding that this amplification is happening because this NMOS is converting the voltage to a current. That current is flowing through a combination of two resistors, RO1 and RO2, leading to a gain given by GM1 RO1 parallel RO2. Sorry, Anand, what was your question?
So what if you had shorted VP and VN to the same ACC?
That's what you're going to do next. So you can do it. Short VP and VDD and tell me if the answer will be any different. Do you expect the small signal gain to change?
Yes, sir, because like then VGS2 will not be 0.
If VP and VDD are equal.
No, sir. I was saying, what if we shorted VN and VG?
So we'll do that now, and then you can tell me. So let's do that circuit since you wanted it. Let's do that circuit. So you guys go and figure out what the gain of this circuit is.
So instead of GM1, we'll just end up with GM1 plus GM2.
Very good. You can argue that without even solving the circuit. So it's up to you guys how you want to think. Let's do it both ways. So find the gain of the circuit, RN and R out. Again, assume both M1, M2 are in saturation.
So that's where my doubt was. Won't it be like GM1 minus GM2 into R0 parallel?
Minus or plus?
I was actually getting confused with the minus. That's right.
But that's what I'm asking you. Why are you getting confused? So the answer should be minus GM1 plus GM2 into RO1 parallel RO2. Rn is infinity. R out is RO1 parallel RO2. So can somebody, I want to get to it, we will solve this, and it's 10:48 already, so we may solve the small signal model next class. But can somebody argue with me without doing the small signal analysis and quickly arrive at the gain? Can somebody explain how I can write this gain directly without actually doing the small signal?
So,
attempt.
Both the resistors are connected between Vout and ground.
Okay.
And one current is GM1 and the other one is GM2. So the total current will be the sum into the.
Good. So the difference between this circuit and the previous circuit. So if you look at the only difference we've done is we have connected the input signal to both the PMOS and the NMOS. So again, remember how the common source works. The common source topology works because an input voltage is converted to a drain current, which flows through an output resistance, leading to a gain, right? So in the previous case, right, if you look at this case, when I connected an input, when I connected my input voltage, only M1 was converting Vn to a current, right? So the current that was being flown because of this, that is the essential transconductance of the MOSFET, right? The MOSFET is a transconductance device. So M1 is doing the job of converting the input signal voltage to a current, and that current flows through the resistors, right? R01 parallel R02. Hence, we get the gain GM1 times R01 parallel R02. Now, in the case when both the transistors are connected to signal, right? What happens? Both the transistors are converting the input signal to a current, right? So Vn, when you apply it to M1 gate, right? M1 is converting Vn using minus GM1 Vn. Right? Similarly, M2, now the reason, Anant, why it adds and not differentiates is because this is a PMOS and this is NMOS, right? So for example, let me suppose Vn increases. If Vn increases, what happens to the current flowing through M1? Will it increase or decrease? If Vn increases, what happens to current flowing through M1?
So it increases.
It will increase, right? Similarly, if Vn increases, what happens to the current flowing through M2?
It will decrease.
It will decrease, right? But eventually what happens is that when Vn is going up, right, this current is going to flow, so both the currents are going to flow in the same direction. And so therefore what happens is that when you're applying Vn, right, M1 is converting it to minus GmVn, M2 is converting it to the same current flowing in the same direction, right? So M2 and M1 both are converting the voltage to a current. So the net current that is being converted because of this combination is a sum of the two currents, GM1 plus GM2, right? Hence, what you see is that in the previous case, when you just connected to the NMOS, right, there was only one current. So GM1 was the only one which was contributing to the current, which was flowing through this parallel combination. However, when you look at, you've connected the signal source to both the transistors are converting to current. So you have an additional current flowing in this, additional small signal current flowing in the circuit because of both NMOS and PMOS together. Hence, the gain goes up because you have both GM1 and GM2 contributing to current, right? So the gain in this circuit is going to be much larger than the gain in a common source configuration, right? So purely from the gain point of view, this is a better signal, and this is nothing but an inverter. So this is the reason why we use this as a static CMOS inverter in DD, and the reason being because this inverter has a high gain, so quickly switches from VDD to V0. Analog design, we won't use this much. As we go through the class, you'll understand why we don't like a design like this. But for now, just know that this will have a high gain. So what we'll do is in the next class, I'll start with doing the small signal analysis of the circuit, and then we'll go on to figuring out how do we use other loads instead of the PMOS saturation, and see what happens to gains if I use different kinds of current loads. Okay. So I'll stop here and I'll take any questions that you guys might have.
Sir, can you show the small signal model of 2?